Like I was saying, I'm Drew. I'm a graduate student here at McMaster University, and I'm here to talk to you about exoplanet detection, about how we find them and in what ways. So, to start, let's go ahead and look at the distribution of how we found exoplanets. Ever since the first one was discovered, all the way back in the 90s, we've been looking for exoplanets up in the sky, and we've been finding them at an exponential rate. As of today, we found a hair under 6,000 exoplanets, which means that we've been finding one every day or so for the last several years. Not a bad rate. And so if we look at this plot here, which shows the cumulative number of exoplanets discovered every year over time, we can just see that we've been discovering more and more. And we can see what discovery methods we're using to find most of them. And we're going to go through a few of these. With these two, the purple and the green ones right here, most especially. And we're just going to go through them in rough order of most common to least. So to start off, the most common method for finding exoplanets is called the transit method. So imagine you're looking at a light really far away, so far away, like the stars in the sky, that you can only really see them as single points. Now imagine somebody standing next to the light decided to cover half of it up. You see the light get a little bit dimmer, right? And if you saw the light suddenly get dimmer out of nowhere, you might
Start
say it
completely.
must be covering it up.
It's exact 10 p.m.
And stars work the exact same way. If a planet orbiting a star happens to line up just right, it's going to do what's called transit the star, which is a fancy way of saying just pass in front of it. And then it's going to block some of the star's light, and we can see a sudden dip in how bright the star appears. And then after the planet passes away, we're going to see the star brighten up again. What's more, we know that bigger planets are going to block out more light, so we can get a pretty good estimate of how big this planet is by how much the star dips. And so we can learn from these sorts of measurements. We get what are called light curves, which are essentially time resolved photometry measurements. So a fancy way of saying we get a big data set of how bright the star is at every moment in time. And so when we do that, we can learn a few different things about these exoplanets. So the main things we can learn about these exoplanets are the planet's period and the planet's radius. So the period of the exoplanet is pretty simple. If we go back, we can see that the planet goes in front of the star, transits the star, every one time it goes around. So every one period. So if the planet transits every, say, 10 days, we know the planet's period must be 10 days long. We can also figure out the planet's radius by seeing how much the star dims. And to do that, we take a measurement of what's called the transit dim. This is just a method of saying how much the star dims as a fraction of the star's brightness. And it's often denoted with either a z, like this, or sometimes a d or a delta. And we can calculate it with this equation right here. The transit depth is just the radius of the planet over the radius of the star squared. That's essentially equal to saying the cross-sectional area of the planet divided by the cross-sectional area of the star. And this value is really small. For a Jupiter-sized planet, which is, about as big a planet as we expect to see, this transit depth is only going to be about 1%. This planet is only going to go ahead, or the star is only going to go ahead and get 1% dimmer. And for an Earth-sized planet, that number is more like 0.01%. And so as a result, we can get a really good estimate of the planet's radius, or at least the planet's radius relative to the star's radius. But normally we know the radius and the mass, for that matter, of a star is within a couple percent, just from how bright it is and what spectral type it is. So we can get a pretty good estimate of the planet's radius. The last thing that we can learn is the planet's inclination. See, the inclination of a planet essentially tells you what orientation the planet's orbit is relative to our point of view. So as a planet orbits a star, it can go what's called edge on, meaning the planet, if we look at the plane in which the planet orbits, we can only see the edge of it. Or it can be face on, whereas the planet goes around like this, where we can see the entire plane the planet orbits in. And the inclination essentially determines this value. If a planet is edge on, so we can just see the edge of its orbiting plane, we call that to have an inclination of 90 degrees. And if a planet is face on, that has an inclination of 0. And anywhere in between is anywhere in between. And this is interesting because we can only see the planet transit if it's edge on. If a planet goes like this, we're not going to be able to see it transit because it never passes in front of the star. But if it goes like this, it passes in front of the star, and so we're going to be able to see it transit. And so a planet can transit if and only if it has an inclination of very near 90 degrees. Depends on the exact planet, but it can typically get to up to like a degree or two away while still being transit. And so we can learn the planet's inclination. That's often not helpful because we can only see planets of one inclination. And that means that while we can see a lot of planets transit, the vast, vast majority of planets don't transit at all. And we can calculate the probability of a planet transit with this equation right here. E subtransit, so the probability of a planet transiting, is roughly equal to the star's radius over A, where A is a semi-major axis of the planet. The semi-major axis of a planet is essentially the planet's average distance from the star. And this is a small value. For a planet like the Earth, this value is only about 1 in 200, meaning the vast, vast majority of planets don't actually transit. Now, we can also look at a graph like this to get an idea of what sort of planets transit and what sort of planets we're going to see with this method. So this is a plot of the planet's mass, or minimum mass, which is a similar thing that we'll talk about in a sec, versus the planet's orbital period. So the length of its year around the sun, around its star. And all the dots that are in purple circles, those are planets that we've detected transiting. And if we look, we can see the vast majority of planets that we detect through transiting have a really short period, in the days or the tens of days long. And that's no accident. Because of this method right here, this equation right here, we can only see planets that are shorter periods and thus closer to their star. They're a lot more likely to transit, and so we're a lot more likely to see these planets over here. Also, on a more practical note, we got to be able to see a planet transit many, many times in order to be able to determine its period. And if a planet has a period of, say, 1,000 days, we need 2,000 or 3,000 days to see it transit multiple times. And oftentimes we just haven't been observing for that long. So this transit method is very good at getting the radius and the period of planets, but it can only be used on these shorter planets, shorter period planets. And if we look at the distribution of how many planets we've discovered through each method over time, we see the vast majority of these planets that we've discovered have been with the transit method. We see, especially over recent years, we've been detecting most planets, not just transiting, but transiting because of 2 separate telescopes, Kepler and TESS. Kepler was the first telescope sent up into space to really discover a huge amount of transiting, launched in 2009 and going all the way until 2018. And you can see here, it just stared up at one patch of the sky for years and years and discovered the vast majority of planets. And then afterwards, after it died in 2018, right around that time, we launched the TESS telescope, the Transiting Exoplanet Survey Satellite, which has been observing the entire sky. So it's not able to get as good data on one particular section, but it's able to observe the entire sky and find hundreds and hundreds of planets ever since that time. But if we look at something like this, we can see that there's another method here, not just the purple transits, but this green method that's responsible for discovering a huge chunk of these planets. And this is the radial velocity. Let's talk about that one. So, have you guys heard of something called the Doppler effect before? So, okay, so it looks like a couple of you guys have. But just in case, for people who haven't, the Doppler effect is essentially a source of light getting redder or bluer if the source of the light moves towards or away from you, the observer. If something's moving away from you, it's going to get what's called redshifted, meaning the entire source of light looks a little bit redder. And if it's moving towards you, it's going to look a little bit bluer. And this is something we can actually measure. And so this transit or this radial velocity method measures a star getting slightly redder or slightly bluer as the planet orbiting around the star causes the star to wobble back and forth. And we can see what that looks like here. The star or the planet goes around the star, and the planet obviously has huge shifts in movement over time. But the star is going to be pulled back and forth a little bit as the planet goes around it. And we can actually measure that. It means the star gets a tiny, tiny bit redder or bluer, and we can see it. We can use this equation right here, although it's really not relevant at the moment, to measure what is a new wavelength, how much a wavelength of light gets shifted as a planet moves towards or away from the star. You don't need to memorize this equation, but the important thing is that the planet or the star, its light only gets shifted a tiny, tiny, tiny bit. Yes, exactly, Taha. The star's movement is highly exaggerated. For example, if we see a wavelength of light, the star emitting light at about 1 micron, and we look as we see how much the planet is gonna, as like an Earth-sized planet goes around the star, we'll say it's close to its star, so it's a pretty big shift. Light at about 1 micron, so about 10,000 angstroms, is going to get shifted over to about 10,000.3 angstroms. This light is only getting shifted a tiny, tiny, tiny amount, but we can actually measure it. The best instruments in the world, instruments like HARPS or NIRPS, or other spectrographs like Maroon X or Espresso, all have the precision to measure shifts in the star's velocity as small as about 1 meter per second. 1 meter per second is like walking speed. If you were like standing in front of the telescope, it could tell just by your Doppler shift if you were moving towards or away from it at walking speed. And instruments being built right now are going to get even better. The instruments being built right now that should be ready by 2030-ish should be able to reach a precision of about 10 centimeters per second, an order of magnitude better than we already have. And you can see over here what a radial velocity curve looks like for a planet going around a star. This is actually the first planet around a main sequence star we've ever discovered, called 51 Pegasi b. And this is a big planet, like a Jupiter-sized planet, really close to its star. And we can see it going back and forth, the star going back and forth as it orbits. And very shortly, we can measure the period of the planet by looking how long there are in between the valleys or the crests of the almost sinusoidal shapes that the planets are going to make. Actually, if the planet is in a perfectly circular orbit, it is going to be perfectly sinusoidal. And what's more, by measuring the height or the semi-amplitude k, so the distance between the average radial velocity and the peak of this curve, we can measure what the mass of the planet is. So, Harish, ain't redshift an expansion of the universe? Yes, it is. Most of the planets, all the planets that we're discovering are in our galaxy, meaning there's basically no redshift from the expansion of the universe we got to worry about. And Cosmo Boy, what's the phase in the x-axis? That's a fancy way of saying the phase of the fraction of the planet's orbit around the star. A planet has a phase between 0 and 1, and so this right here is 1 orbit. So this method can tell us the period of a planet, and not the mass of a planet, but the minimum mass. See, for a planet, if we're looking at transits, a planet needs to have an inclination of exactly 90 in order to be detected with transits. But that's not the case for radial velocities. If it's just a little bit off, instead of the star going back and forth, like towards and away from you, it's going to go towards and away from you, but also a little bit up or down. And we can still measure that. But we can't measure the actual mass of the planet if it has an inclination like that. What we can measure is the x component of that movement back and forth. And so it turns out we can't measure the mass, but we can measure m sine I, so the mass times the sine of the inclination. And so if a planet is also transiting, then we know I is 90, and so sine of I is 1. But oftentimes we don't know that, and so we can only measure the minimum mass of the planet. It could be larger if it's at a very low inclination orbit, but we don't quite know what it is unless we have another way to measure it. The last thing we can measure with this method is the eccentricity of the planet's orbit. See, most planets are going to orbit in an eccentricity of nearly 0, meaning they go around their star basically in a perfect circle. And if that happens, the planet's orbit, or this radial velocity curve, is going to be basically perfectly sinusoidal, meaning it's like a sine shape. But if it has a high eccentricity, its radial velocity curve is going to diverge more and more away from a sine. If it has an eccentricity of 0.3, which is about the eccentricity of something like Mercury, it's going to have a radial velocity curve like this, which almost looks sinusoidal, but not quite. Similarly, if we increase its eccentricity even more, it's going to be moving really fast or really close to its star at some points, and really slow and really far away. And the star is going to be doing the same. It's going to have these big spikes in radial velocity, followed by basically no signal outside of that. And of course, the shape of this is also dependent on longitude of periastron, which we don't need to worry about here. It's basically saying how aligned the orbit of the planet is in a different way than the inclination. But we don't really care about that here. So the last thing we want to talk about with radial velocities is this equation right here. If a planet is on a circular orbit, which for most planets is a reasonable assumption, this tells us the semi-amplitude of the planet's orbit. So once again, the semi-amplitude is half of the height between crest and trough of the radial velocity curve. So between 0 and its height. And this is the equation right here. We have the K, the semi-amplitude, is equal to the minimum mass of the planet times the cube root of 2 pi times, the gravitational constant over the planet's period and the stellar mass squared. This means this method is going to be better at finding low mass planets. It's going to be better at finding close planets, so short period planets, and really big planets. And if we look at this curve again, we can see that the planets we see, Mohammed, so the more mass of a planet, the more it transits. No, we're not talking about transits here. We're talking about radial velocities. The more mass of a planet, the bigger a radial velocity curve is going to be. The higher the amplitude of this radial velocity curve over time. And the limit of the sort of planets we can detect here roughly correspond to this red line right here, which if you do the math, K, once again, is the semi-amplitude of the planet's orbit, of the radial velocity curve, sorry. So it's the distance between 0 and the height of this radial velocity curve. If we plot all the radial velocities of the star over time. So right here, this K would be 55, 56 meters per second. Correct. Yeah. So this equation, you're going to want to know if you're doing any sort of radial velocity stuff. But if we look at this plot, we can see that all the planets we've discovered with the radial velocity method sort of tap out right around this line. We can mostly only find planets above it. And if we do the math, it turns out that this line roughly corresponds to a semi-amplitude of 1 meter per second. And so we can mostly only discover planets that have a high semi-amplitude. The best instruments in the world can reach a precision of about 1 meter per second. So it makes sense we have a lot of trouble finding planets with a lower radial velocity. But like I said, we're getting better and better telescopes. We should be able to discover, or better and better instruments. So we should be able to discover more and more planets pretty soon. And yes, exactly, Lavanya. If a star is more massive, it's going to have a lower semi-amplitude. So both these methods, the transit and the radial velocity method, are both sensitive to planets around lower mass and lower radius stars. All the smallest planets we discover, the ones right down here, are for the most part planets around really low mass stars like red dwarfs. And in your assignment later, you guys are going to be going ahead and looking at synthetic radial velocity and transit data and trying to characterize the mass and radius of a planet around one of these low mass stars yourself. So there are a few other methods of finding exoplanets. If we look at this plot right, there are all these little methods right up here. The radial velocity and the transit method make up like 95% of planets we found. So we're just going to ever so quickly go through the other methods that we've used to find planets, rapid fire. So yeah, Avi, exactly. With better instruments, we're going to be able to extend into the lower right section of this graph over here. So, rapid fire. The next method of finding exoplanets is the microlensing method. So have you guys heard of gravitational lensing? If not, it's, in short, a star from really far away emits light at us, and a planet or or a star or any sort of massive thing in between the source of light and us happens to lie just in between us, and it kind of gravitationally focuses the light straight towards us. There's macrolensing, which can gravitationally lens the light of a galaxy by another galaxy. But there's also microlensing, where a star gravitationally lenses light from a star. And we can't actually see the lensing. We usually can't see the source in between us. But we can see the star behind it get brighter, get more magnified. And so that'll produce a curve like this, where we see a star all of a sudden get up to 2 or 3 times brighter over a period of days or weeks. But if that star right here in the middle has a planet, then that planet can also do a little bit of microlensing. And so while the star has a huge curve like this, the planet produces a tiny little magnification spike like this, where for a period of like hours, we can see this star, or the star behind it, the source of the light, get a lot brighter. And so we can use this method to detect exoplanets. Once, because this is all premised on the idea we can't actually see the source of light right here, the lens, as it's called. And so we can detect that an exoplanet exists with this method, but we can't really do any further studies on it. We just know the exoplanet exists, and then it's gone forever. But the good news is, this method, without getting into all the math behind it, it's actually really sensitive to finding planets. In this method of this graph, it turns out that this method is sensitive to finding planets that are about the distance of the Earth or Mars away from the sun. And if we look at all the planets we found with this method, microlensing, they all lie right over here. So while this method sucks because we can only do statistical analysis, we can't actually further characterize any one planet, this can tell us a lot about the planets over here, which transits and radial velocities have trouble detecting. The next method is transit timing variation. As a planet goes around a star, this planet is going to transit a star once every period. If its period is, 1 month, it's going to transit a star exactly once a month. But, oh great, this was an animation that was supposed to play. But if the planet has other planets in its own star system, those other planets are going to pull on the planet with gravity. And so their gravitational force is going to cause the first planet, the one that we can see transiting, to transit hours or minutes up before or after we expect it to. And we can make a plot like this of how much earlier or later it transits than expected. Plot of its transit times. And we can do a whole bunch of expensive math and computation to try to recover. Well, okay, we see this weird curve. We see this planet transiting before or ahead of expected, or before or after expected. Can we use that to recover how the planets that we can't see, the planets that are causing these transit times? And the answer is yes, we can. But it's really difficult, so we're not going to spend too much time on it. The next method is called astrometry. This is a cousin of radial velocity, where instead of measuring the planet moving back and forth, we can actually observe the star going from side to side. This is a method where we can observe the change in location of the star due to the planet motion, but the star's actual location, like left or right tangentially, instead of towards or away from us. So as the star moves, it has its own proper motion throughout the galaxy, which is, a straight line through space. There's going to be a big sinusoidal shape, or a big loop-de-loop shape, caused by the motion of the Earth. And as the Earth moves, the star is going to appear to move position because of parallax. But the star is going to also be wobbling a little bit, slowly moving throughout space, because of the motion of a planet, typically a big planet. And we can actually observe this, in theory. So, in theory, because it turns out that getting this data is really, really hard. We need really, really, really precise motion of the movement of these stars to the tune of like, if you guys know what an arcsecond is, to the tune of like a micro arcsecond. But we can get that in some situations, especially from the Gaia telescope. It's a big telescope whose job for the last 10 years or so has just been to look up into space and get really precise position at every star in the sky. And it stopped running a month or two ago. But its final data set should be coming out next year. And it will just come out with a whole bunch of planets that we've detected through this method. We've detected 5 planets right now through the astrometry method. This method will go ahead and discover about 10-ish, 10,000 or so new planets by the end of next year. And similarly to the microlensing methods, this method is really, really good. The astrometry method is really, really good at finding medium period planets. It turns out that a longer period planet is actually going to create a bigger wobble, so it's going to be easier to detect. But we only have like 10 years of data, so planet can't exactly have a period longer than a couple of years, or I won't be able to see it go through at its full orbit. And so this method is really good at finding, just like microlensing, longer period planets, but not too long. The last and final method, and then I'll let the other person talk, is the direct imaging. So this is a method where we just say, screw transits, screw radial velocities, let's just look at the planet directly. We get a big telescope, like the biggest in the world, and we just stare at a planet or a star that we think should have planets. And we use something called a coronagraph, so a big metal disc, to actually block out the star. So we're only left by seeing the planets over here. And if we do it just right, and they're really big, really bright, really hot planets that are far away from their star, we can actually see them over years and years go around their star. Like this is a video of HR 8799, the star, and it's 4 planets that all seem to be going around the star. And this can tell us the period of the planet based on how long it takes to go around, and a rough idea of the planet's mass based on how big it would have to be as bright as it is. But this method only works on planets that are really far away from their stars, like Uranus or Neptune distance at a minimum. These ones are way further than anything we have in our own solar system. And only really big planets. But if a planet has to be really big and really hot and really far away, these planets have to be really, really young because they start out hot and slowly cool down over time. So this method couldn't be used to find any planets in our own solar system. But for stars that are just forming planets for the first time, we might be able to find some. And because we want planets that are really far away, this is the best way to find planets that are really, really far away from their host star. Like planets that have an orbital period of 1 million or 10 million days. Planets that are so much further out than anything in our own solar system that they're only barely gravitationally bound to their host stars. Because we like this method excels at seeing those really far away planets, which, as tough as it is to do, we just don't really have any other way of finding. Yeah, that ultimately concludes my presentation about finding these planets. Like I said, the transit and the radial velocity method are the ones that find the vast, vast majority of planets. And so those are the two that you guys are going to be working on in your assignment. Your assignment is going to have you looking at fake radial velocity and transit data around a low mass star and trying to figure out what the mass and radius and thus the composition of these planets are. But for now, do you guys have any questions?
Thank you, Drew, for a phenomenal presentation. Yeah, let's have some time for questions.
Yeah.
Please
So,
raise
Mohammed,
your hand. Okay.
yeah. People can raise their hand, and until people do, I'll go ahead and answer them in chat. So first, Mohammed, did you say fake data? Yes, you are going to be going ahead and working with fake data for this assignment, not real data, just because real data is really tough to work with a lot of the time. Yeah, Avi, you have a question?
Yes, I seem to recall hearing from someone that for transits that you get a second drop from I think the infrared for the when it goes behind the star. Is that correct?
Technically yes, but not in reality.
Oh,
So the question was, if you have a transit like this, you have a dip in brightness from the, oh, wrong plot, a dip in brightness from the planet passing in front of the star. But if the planet emits some brightness, as the planet passes behind the star, it should, in theory, produce a dip too. And that does happen. The issue is stars are a lot brighter than planets. So the dip from the planet passing in front of the star is a lot dimmer than the reverse. But if we have really, really big planets, like hot Jupiter, so planets that are really hot, Jupiter-sized, really close to their stars, that it's something we can measure, yes. But for most planets, it's not the question.
Good to know. Thanks.
Siddharth, do you have a question?
Yes, sir. So my question is that can we use the transit method to find stars find the planets in a variable star, like any Cepheid?
Yes, absolutely. And we have detected a lot of planets around a variable star. This light curve, this plot of brightness over time, would look different because the brightness from the change in brightness from a variable star would dominate the change in flux instead of the planet transit. But we should, in theory, be able to measure both because they look different. It just means that instead of seeing a transit that looks like this, we'll see, the planet's brightness change in time, or the star's brightness change in time, and then there will be a little bit of a transit like that we'll be able to see. Make sense?
Yes, sir. Makes sense. Thank you.
Perfect. All right. Let's answer a couple questions from chat real quick then, if nobody else is raising their hands. So aren't these planets? It looks like most of the questions have been answered already, actually. So in that case, I'm not sure which how many I have to answer. Rashmika, do you please explain the assignment? It wasn't clear to me. Very briefly, although the assignment itself will have instructions on it, the assignment is going to have you working with fake data, so fake light curves like this, and fake radial velocity curves like this. And it's going to have you looking at these curves and using equations like this. Might want to write this one down. To go ahead and calculate the mass and radius of a fake planet that you can see in the data. And because that's the sort of thing that us astronomers are trying to detect planets too. Normally we have computers that are working with this, but you guys aren't supposed to know Python or any sort of fitting methods yet. So to answer Siddharth's question, they're not going to be given as a CSV file or a FITS file. You're just going to be looking at the actual plots and interpreting from there. So John, what happens when you use the transit method, but the planet doesn't really have an effect on the light of a star that's too small? The answer is we don't detect the planet. If we look at the plot of planets right here, we can't really detect any planets smaller than roughly Earth mass, which corresponds to roughly Earth size too. That's because once you get below that, the planet's effect in the star is just too small for us to be able to measure. So it's easier to measure big planets with this method, and there's a fundamental method in limiting the size of these stars, the size of the planets we can detect. Rudra and Vidisha, how does this method help us finding the inclination of the planet? So the inclination of the planet essentially tells you the planet's orientation around the star. It can range from 0 degrees to where this planet is quote unquote face on, so where we can see the entire planet go around the star, versus 90 degrees, where the planet is quote unquote edge on. And if a planet is transiting, it has to be edge on. So a planet like this right here just straight up does not transit. And so it turns out that if a planet is transiting, it has to have an inclination of basically exactly 90 degrees. Depending on the star, depending on the planet, and how close the planet is to the star, it can be 90 degrees plus or minus a couple of degrees. So it could be, 88 or 89, but it basically has to be 90 degrees or very close to it in order to transit. So let's looking at the other question. So Anindya, is there any sorts of getting real data? Yes, I believe later on, when you will be working with a code called a Radial to measure radial velocities, later on this semester, I'm pretty sure you're going to be working with real data there, although I'm not 100% sure. But there are plenty of sources you can go ahead and get real light curve data to mess around. There's code called light curve or Eleanor, which are 2 Python packages that are designed to let you get data from Kepler and TESS, like open source data. And there are plenty of other codes you can use to find or download that data online. Mohammed, just all the exoplanet discoveries have somehow uniform orbital periods. Yes, in the sense that the planet's orbital period doesn't change throughout time. Sometimes it will ever so slightly, like this transit timing variations method we talked about. It will transit, so its period will be shortened or lengthened by minutes or hours. But outside of that, planets will have the same orbital period over years. Over long periods of time, the planets can evolve and slowly change orbital periods. But that's a long-term issue. So yeah, Deepak, is high eccentricity very common in exoplanets? No, not really. Most exoplanets we've discovered have low eccentricities, so less than about 0.1. That said, there are planets that have very high eccentricities that we have discovered. And this radial velocity method is the easiest way to figure out their eccentricity. So, Sukriya, isn't direct imaging limited? Can we see planets really far away? Padma. Yes, it is really difficult. Sutria, does transit also depend on the distance between the star and the planet rather than just orientation? Not really. It turns out the distance between the star and the planet doesn't actually matter for how big the transits are. It's so far away, the star, that the little distance between the star and the planet doesn't really affect anything. That said, it does affect the odds of a planet actually transiting and thus being visible in the first place, using this equation right here. Last question, agreement. To measure an exoplanet's inclination, the telescope on Earth always be pointing towards the exoplanet star? Not really. The way we're going to detect the inclination of a planet, the main way that we detect inclinations of a planet is with the transit method. So if a planet is transiting, then we know its inclination is 90 degrees, basically exactly. With a method like the radial velocity method, we can't actually determine the planet's inclination. With other methods, like say, like microlensing or the transit timing variation, you can get constraints to the planet's inclination. But like we said, that's really tough to do. The main way you can get a planet's inclination outside of this method, actually, yeah, that's really about it. Finding an inclination of a planet is a really tough thing.